A P&ID is also expected to show fittings. We should also add reducers and enlargers. For example, we have a 6-inch pipe and we need to connect it 4-inch pipe. So we shall need a reducer to connect both pipes. And if we want to connect a 4-inch pipe to a 6-inch pipe, we would need another enlarger. So if we want to connect two lines, two nozzles with different sizes, we shall need a reducer or an enlarger. Otherwise, there shall be a conflict in the P&ID as these cannot be connected. New drawing software such as SmartPlant can easily detect these issues. Adding reducers commonly used to connect equipment or instruments. A common example is connecting a control valve pipe, as in most cases the size of control valve is smaller than the size of the pipe. So we shall need a reducer at the valve inlet and an enlarger at the valve outlet. So we have seen that reducers and enlargers connect pipes with different sizes. But what if we want to connect flanges with different ratings? We shall use class breaks to solve this issue. For example, we want to connect piping with flange rating of 150 pounds to piping with a flange rating of 300 pounds. We shall use class break in this case, and it shall look this way on the P&ID. This is because a flange with a rating of 150 pounds will have less bolts than a 300-pound flange. That's why we can't connect these flanges. So we shall need 150-pound rating flange with the same bolt in order to connect them to the other 300 pound. But why would we need to connect two pipes with a different rating? There are two main reasons. The first reason is to connect a piece of equipment or an instrument coming with a different rating. This is highly common with pumps, for example. So we may see that the nozzle of the pump has a higher rating than the suction and discharge piping. In this case, we shall add a class break on both suction and discharge piping in order to connect the nozzle's piping. The second reason can be when we connect a high pressure system to a low pressure system, which are called also high to low pressure interfaces. So for example, we are having here a back pressure controller that keeps the upstream pressure at a specified value. Maybe to adjust operation of the reactor, maybe adjust pressure of the tower, whatever the equipment is. But after the control valve, we don't need this pressure. Maybe the fluid shall go to a storage tank at an atmospheric pressure or to a downstream system that is already working at much lower pressure. In this case, we don't need the downstream system to have a high thickness or a high flange rating, as this shall mean much higher cost. So in this case, we are considering a design pressure upstream the control valve, for example, 30 bar gauge, and the design pressure downstream the valve shall be only 3 bar gauge. And as the upstream pressure has a flange rating of 300, we shall also add a class break downstream the isolation valve. So after the control valve, we shall add this class break so that the downstream system shall consider a flange rating of 150. Here comes a safety issue. What if the control valve fails in the open position? This shall mean that the whole downstream system shall be subject to the high pressure, which may lead to a mechanical failure in the downstream system and may lead to major catastrophes. That's why this system must be protected, whether by a pressure safety valve or by a shutdown valve in the upstream system that shall close once a high pressure reading is triggered. We shall see how these systems work in later videos. There is also an important fitting that should be shown on a P&ID. Here we are talking about a spectacle blind. The spectacle blind has two faces. One is at open position, where the flow can pass normally, and the other is at closed position with a blind flange that totally blocks, and there is no probability of having the fluid passing through the system in this case. During maintenance activities, the operator shall take the blind out and switch its position on the pipe from the open position to the closed position. This is called positive isolation and is used to ensure that the downstream system shall be totally isolated from the upstream pressurized fluid so that we can now carry out the maintenance activity that we need. The blind is usually an integral part containing both open and closed positions. If the pipe size is too large, the spectacle blind shall be heavy, be removed by the operator. That's why it's preferred that at a pipe size of 12 inches or larger, and depending on the standard of the company, the spectacle blind shall be separated into two parts, the spade and the spacer. Now let's move to T-fittings. In a P&ID, and as it is already showing all piping, T-fittings shall be shown, whether they are for branching from a pipe or a pipe that is connected to another pipe. These T connections should be considered when calculating the pressure drop in a pipe. Another fitting that we should consider in P&ID is the insulation kit. The insulation kits are needed when we want to connect two pipes with two different materials of construction and there is a probability of galvanic corrosion.
Now, it's important here to highlight that not all piping or fitting details are shown on the P&IDs. In general, the P&IDs are schematic drawings. This means that they are neither drawn to scale nor required to show the exact pipe direction in the 3D model or in the isometrics, which should match the situation in reality. So the direction of flow may be different in the P&IDs with respect to the north. Even some mismatch in branching with the 3D model can be tolerated if it doesn't impact the operation. That's why we don't show pipe length or distance in the P&IDs. We don't show elbows either. The exception to the above is usually the distribution P&IDs, showing, for example, the collecting header of relief lines, which should be shown exactly as they can affect the flare back pressure and the operability of the flare, which can cause a safety issue as pressure safety valves may not be able to protect the plant in case of high flare back pressure. Also, the distribution of other utilities is highly preferred to match the plot plan.